So let's look at a couple of examples of using DCT. Here we have something 1 over n to the 4th plus 1 from 1 to infinity. Again, as we're going through series, think in terms of strategy. We're kind of building up a list of possible approaches, and we need to get good at spotting when to use them. So let's think about what we know already. We know about geometric series. That does not look geometric. Remember, geometric is a constant to the n, essentially. Doesn't look to be geometric. Telescoping looks like the same function twice, subtracted but shifted by 1. There's no subtraction going on there, so probably not telescoping. We learned about the nth term test. Well, if you look at these terms, they're clearly going to 0. That bottom's just growing and growing. 1 is fixed, so nth term test is going to be inconclusive. Integral test. Now we could possibly do integral test because the function 1 over x to the 4th plus 1 is positive, decreasing, continuous. But we'd have to figure out how to integrate 1 over x to the 4th plus 1, which I'm not sure if we know how to do that. But it's very, very close to being a p-series, right? It's not a p-series, but it's just off by a smidge there. So when you see something that looks almost like something you could deal with, but it's just shifted a little bit, then DCT is probably the way to go, or LCT, which we'll look at in a minute. So yeah, this is very, very close to being 1 over n to the 4th. And how does it relate? Adding that 1 makes the denominator just a little bit bigger, meaning that it's just a little bit smaller than 1 over n to the 4th, right? And those terms are all greater than or equal to 0. So I'm just stating the inequality, right? Remember, we need our terms need to be non-negative. So these guys are non-negative. That's why I put the 0 there. So I want to see you say that, so you understand that we can only do DCT on stuff that is non-negative. And then this is showing the inequality as far as what I'm going to compare with. Okay. But this is a p-series, and we know that the series of 1 over n to the 4th converges. That's a convergent p-series. P is 4, which is bigger than 1. Remember, that was the criteria for a p-series to converge. That exponent needs to be greater than 1. So we've got everything here, right? We're smaller than that convergent. So we conclude that our series 1 over n to the 4th plus 1 from 1 to infinity converges by direct comparison test, or DCT for short. So now you see what I mean about typically you'll compare with a p-series just because it's nice and easy. The reason I can do a p-series here is this is very close to being a p-series, so it's very obvious that this inequality holds. If this was some completely different looking function, say tan inverse, I don't know how it relates to that p-series, so I wouldn't be doing this comparison. But you're looking at something that's very, very close to that, so the inequality is obvious. Okay, let's look at this example over here, 1 over n 2 to the n. So your first idea might be, after having seen that one, that this has a p-series in it, right? 1 over n is a p-series. It's just got a little bit extra there. So your first thought might be, well, let me compare with 1 over n. And by multiplying this 2 to the n is a number bigger than 1, so it's going to make this denominator bigger, making this smaller than 1 over n, right? When I multiply by this number here, this makes this denominator even larger. So that's smaller than that. And so we've got the inequality, right? Those are non-negative terms. We've compared it with a p-series. But here's the problem. That's a divergent p-series. And being smaller than a divergent doesn't tell us anything. So this is going to be inconclusive. This is no good as far as DCT is concerned. But I mentioned previously that besides p-series, another easy thing to compare with is geometric. So yes, there is a p-series in here, but there's also, that's a geometric series, right? Multiplying by that n makes this a little bit smaller than, so let's ditch that. What about arguing this? So multiplying by that n on the bottom makes that, and when n will be 1, they're exactly the same. But after n is 1, 2, 3, 4, this is smaller than this. Now we've got something, because this is a convergent geometric. So we're smaller than a convergent, so we can make our conclusion. So we make our argument about the geometric. That's a convergent geometric, because the absolute value of r is a half, which is less than 1. Right, r was a half in this case. So now we have what we want. We've got non-negative terms. This is smaller than a convergent, so by DCT. So typically, I would say 90% of the time, 99% of the time, you'll be comparing with p-series. But geometric is another thing that we have that's easy to compare with. So if you're looking at something that looks almost geometric but has a little bit of extra in it, you might be able to compare with that geometric as well. Both of these were examples of convergent. Next, we'll look at an example of a divergent series by DCT.